ราะไอ้เขาไม่โง่กินดีจะมองแล้ว
ต้องตัดออกครับ
แต่เขาพูดเนี่ยมึงอยากมันจะซีดิ้งได้ไหมเยี่ยมไปร้องหมดเลยนะซีดิ้งไปเรียนไหมแล้วไปเจอไหมมาไปเรียนไปสองไปเรียนหรออะไรสองนั่นแต่ก็ไปเอาเลยเชื่อมั่นใจมันทุกคนเชื่อใจด้วยถ้าไม่ใช่เมื่อผมเชื่อใจเลยแล้วก็พอที่อยู่หลังเลยเบสตะเขาปลาตุกปีเอาปีตะปีตาสองอะไรไม่มีใครออกตัวเลย
ที่พูดอะไรอยู่ข้างหลังเนี่ย
มาแล้วหายแล้วคุณก็
ไม่น่าจอมันสว่างเลยหน้าจอมันสว่างมากเลย
คุณต้องปรับให้มันสว่างครับหรือว่าอะไรผม
เนี่ยหน้าจอสว่าง
มันสว่างไปหรือเปล่าคุณก็ปรับอันนี้ดี exposure เลยแต่ปรับไม่ได้แล้วปรับได้ไหม
ทำได้
คุณเลื่อนเอาขีดเอาให้มันเห็นมืดไปมันก็จะหน้ามืดหรือเปล่าประมาณนั้นนะครับโอเคป่ะYeah. For signal decomposition, you get the energy around 208 megahertz from both. And what they would like to know is that how much is the total energy when we use uranium-235 1 kilogram. Oh my gosh. Okay. Of course, you need to know. How many nuclei or atoms are there in 1 kilogram for uranium-235? Yeah, this would have something to do with the mass of uranium-235. Okay, in uranium-235 you have 235 grams according to the number of nucleons of uranium-235. In 1 mole you would have 235 grams. Okay, but you need to convert the amount of uranium-235 into number of its nuclei. Okay, this could be done by using the Avogadro number 6.022 10 to 23 nuclear proton, and we have 0.235 kilogram per mole according to this number, 235 grams per mole. If you divide it, you're gonna get 2.56 to 6 times 10 to 24 nuclei per kilogram. So if 1 kilogram, you have that amount of nuclei, which is quite large. Million. Okay, million. And in 1 program, we could get the energy by multiplying the number of nuclei with the energy per nuclei. Okay. The typical energy is student is the mega electron volt. The typical energy unit is mega electron volt. So once you multiply it, you're gonna get the energy per kilogram. To pick up 1 kilogram of uranium-235, you will get that amount of energy. Okay. Assume that every nucleus deliver perfect amount of energy, okay, according to the data. Now, let's talk about the world. If we convert every energy source in the world to be nuclear fission process, assume that the world, but this number is not fixed at all. Assume that for a certain year, the world use the energy per year as 4 times 10 to 22. So let's say in the whole year, every country on earth will consume the energy like this, with this amount. So they would like to know how much uranium-235. If we don't generate energy in other form, we use only nuclear fission process. You need to divide it. You divide this. You need this amount of energy that's leaving after numerator, and you divide the number of the amount of energy per kilogram. Okay. You get you see how many kilograms you need to do that. It turns out to be 4.6845 10 to 6 kilograms, so it fits around 4.6 4,684 tons, okay, per year. That's the amount of uranium we have to consume for the whole world. That 4,684 ตันต่อปีนะเอายูเรเนียมมาเผาเบิร์นเล่นมันก็คือพลังงานให้ทั้งโลกใช้ได้ทุกประเทศเลยน่าจะมีประเทศไหนทำนะแล้วก็ขายพลังงานให้ประเทศอื่น if each fission provides 200 megaelectron volt, now is the number from the second group. How much uranium has to undergo fission per unit time to provide? Of course, per unit time means per second, because according to the SI system, we're going to use second as the standard unit for the time. So per time would mean per unit and per second. To provide 3,000 megawatts, right? So it means 3 gigawatts actually of thermal power. So what we need is 3 megawatts, and the unit of watt is actually joule per second, right? So we're going to represent it in joule per second. What we need is in joule per second, 3 gigajoule per second. In the number of uranium-235 in terms of nuclei per kilogram. Okay. And the amount of energy we can get per nucleus like this. Okay. Yeah. This is the amount of energy we want per second. And here is the number of nuclei, which is the result from the former calculation. In this book, they say 200 nuclei. So once you do compute, you're going to get 3.6539 10 to the 5 kilograms, which is not easy to understand, right? We're going to need to use more appropriate unit, which is milligram, okay, and it turns out to be 36 milligram. Okay, it means a big power plant of 3 gigawatts would consume the uranium only 36 milligram per second. It's like very little piece of sugar, okay? Even less than one teaspoon of sugar. Okay. คุณตักน้ำตาลทรายมาจะไม่ถึงช้อนชานั่นใช้ยูเรเนียมแค่นั้นแต่ว่าเลี้ยงได้ถึง3กิกะวัตต์นะครับที่การวิจัยลงผลิตไฟใหญ่เลยครับแค่ประมาณหลัก1กิกนี่เป็นใหญ่มากแล้ว3กิกนี่ใหญ่เข้าไป3 เท่า Okay. In a nuclear fusion reaction, 2 or more small light nuclei combine to form a larger. Now we move to the next topic, which is nuclear fusion. Okay, nuclear fusion has already gone and it's over. So now we move to nuclear fusion, which is in the opposite way, right? To the nuclear fission. We didn't split anything anymore. We combine the small or light atom to be a bigger atom or larger nucleus. But this process has something more complicated than the fission. In the fission case, you just split the big nucleus into 2 smaller nuclei. The complicated thing is you may not get the same pair every time. Okay, you may have different pairs of nuclei. But nuclear fusion could be something even more complicated. You start from very, very tiny process, get bigger nuclei, and they combine together in each step until you arrive at helium-42. Okay, and according to this process, I would say that if you deal with big nuclei, you will get more energy, okay, according to the formula by Albert Einstein, E equal to mc squared. If you deal with more mass, which means a bigger nucleus, you will get more energy. Okay, let's see in the detail. Usually the mass of the final nucleus is less than the sum of the masses of the original nuclei because we get energy from the fusion process. So we would have more mass at the beginning at the input side, and in the output side we would have less mass, but we get more energy in terms of kinetic energy. Okay. There is lots of mass accompanied by release of energy. Okay. We get energy from nuclear fusion. This is what humans expect to have soon. Okay, due to the climate change. If there is no climate change, is there any need for us to use renewable energy or to create to find any other sources of energy? ถ้าเกิดว่าเราเผาคาร์บอนแล้วมันไม่มีควันขโมงโฉงเฉงเลยเรายังจะเผาอยู่ต่อไปไหมแล้วเผาต่อไปใช่ปะถ้าว่ามันไม่มีขีดจำกัดว่าไอ้พวกน้ำมันที่อยู่ใต้ดินมันมีไม่จำกัดบนโลกนี้เราจะหาแหล่งพลังงานอยู่ไหมแล้วทำไมก็อยู่เนี่ยของเราครับมันไม่มีส่งผลทางการสารมันก็จะอยู่ของเราอย่างนี้แต่เนื่องจากพวกคาร์บอนเชคนะครับผมยิ่งดูคลิปอยู่นะครับสารคดีเขาบอกว่าคาร์บอนเชคคือตัวร้ายความคิดของมนุษย์เลยในการหาแหล่งพลังงานเกิดมาสารทำไมมันถึงมาเป็นโซลาร์เซลล์ทำไมถึงต้องเป็นวินเอเนจีทำไมถึงต้องมีพลังงานพลังงานหายเลือดหายเลือดเพราะว่าควันเชนถ้าโลกมันไม่ร้อนขึ้นมนุษย์ก็อยู่อย่างเงี้ยสบายว่าแต่ว่าสมมติว่าลูกคุณประเทศก็เลยลูกของเกียรติแล้วถ้าเกิดในยุคคุณลูกคุณปู่ผมรถดีเซลควันขโมงโฉงเฉงวิ่งบนถนนไม่มีใครว่าไม่สนใจสมัยนี้ไม่ได้แล้วมันวนภาวะมันสะสมพลังงานเรื่องนั้นที่ร้อนที่ครับเริ่มไม่พอใจแล้วมีตำรวจจับควันดำไปแล้ว For example, for energy liberating fusion, reaction, high performance sequence. As I told you, the fusion process is quite complicated. There are several things. Okay, but roughly speaking, it starts from light nucleus to heavier and heavier, larger and larger nuclei. Okay, so protons which can be represented in terms of proton or hydrogen nucleus comprised to form from deuterium H21 or H1 and the proton which is like E01 or beta 01 in terms of beta 1. So we would have also electron and neutrino. You're going to see later why we should have why is there we're going to see later why there is also electron and neutrino, because there is electron number you have to balance in the equation. You're going to see the reason later that why we have electron neutrino at the end of this chapter. Of course, in physics, one of the most important quantities is energy. Okay, you may pay attention to force, to momentum. Energy is also one of the major things. It is hydrogen, okay, and another hydrogen, and they combine together to get deuterium, proton, electron. The way to compute the energy is to find the mass difference from the input side subtracted by the output side. And then you simply use EMC squared. Okay, the other energy is energy. Okay. C squared turns out to be 931.5 megaton per atomic mass. Once you calculate this, okay, you get the energy around 0.9 mega electron volt, which is not large enough for us to do it. Okay. Because we are in the very first stage, okay, we deal with a small nuclei, two small nuclei, okay, only hydrogen or proton. The proton will annihilate electron, okay, because when the proton was created, it removed something. And in that area, if we have electron can be easily found everywhere, right? So one proton catches the electron, it's going to be in neutral, and that will cause the gamma rays. Okay, we get gamma rays from that, and yeah, the whole process can be seen in this figure, in this equation. And once you compute again the energy, okay, we have more mass, okay, after the subtraction, you get energy around 1.9. Now it becomes greater than before. In the second process, once you have deuterium from the former process, but deuterium was created in the first process. In the second process, hydrogen will be combined with deuterium. Okay, deuterium will cause or will, once they are combined together, build up helium. But this helium is not the most stable version. It's not the most stable isotope. It's helium-32, but it's already bigger than that. Okay. When you deal, as I told you, when you deal with heavier nuclei, you may have more energy from EMC squared. Okay. In this case, hydrogen and deuterium output is helium-32 together with gamma ray. You get the energy 5.49. Now you can see that 5.49 is bigger than the first one, which is only 1.9. Okay, now you have bigger nuclei or nucleus in terms of helium-3. Okay, yeah, the process can further develop. ผมก็ไม่รู้ว่านักฟิสิกส์เขาบินไปที่ดวงอาทิตย์ แล้วก็ไม่นั่งเอาตาจ้องดูมีเดียม32หรือเปล่าดูดี2หรือเปล่าเขาทำไมถึงรู้ว่ามันมี2นี้
ปฏิบัติการนี้จำลองได้ในเตาปฏิกรณ์ตรงไหนครับ
อ๋อทำเองบนโลกนี้นะครับไม่ต้องบินไป
เตาปฏิกรณ์ตรงไหนที่ใกล้เคียงกับที่สุด
ชี้มาให้เห็นเลยว่าเป็นที่เรียม32มี21อะไรได้นะโอ้สุดยอดเลยผมนึกว่าเขานั่งเครื่องบินไปที่นู่นครับกว่าจะถึงตัวมัน
อินเดียเพิ่งส่งยานไปพระอาทิตย์มานี่ครับ
ไปถึงพระอาที่เหลือ
ไม่ถึง
ไม่ถึงอ่ะใกล้ๆอ่ะ
ไปถึงก็ตายดิเพราะมันเป็นล้าน
ไปรอบๆ
ล้านองศาเลยใช่เหรอ
ใช่
กลับมาไม่เหลือซากแน่นอนครับไปรอบๆเนาะ
ไปรอบๆอ่ะไปรอบ
โอเคเดี๋ยวเลย
ๆไปวนรอบ
Okay, 5.49. And in the third process, yeah, the outcome was helium-free too, right? But as soon as in that area, we have plenty of hydrogen, or hydrogen nucleus. โอ้ขอโทษครับชีวิตผมพูดเสียงดังไป
โอ้ยแรงเว้ยหลับตั้งแต่เที่ยงสี่
อ๋อเริ่มตั้งแต่เที่ยงคืนแล้วนี่คุณกลับบ้านบ้างแล้วหรือยังครับกลับแล้วเยี่ยมมากครับโอเคไปให้คุณพ่อคุณแม่เห็นหน้าบ้างครับ The third process is that in that area we have plenty of hydrogen nucleus or proton, right? Hydrogen will serve as the material of the heat to the gas. Okay, so hydrogen will combine with helium-free too. Now it turned out to be the most stable nucleus that we have served. One of the most stable nuclei that we have served. It's helium-42 or the actual particle. And here you would have also a proton together with gamma ray. That's one of the products. So this is the reason why we get the light from the sun. Okay, because gamma take place almost every equation. Okay, in this one, except for also in the first process. In the second process, we have also gamma, which is gamma ray, which is a power photon. Even in the third process, we have also gamma ray, and this is the reason why we get the light from the sun due to this kind of thing. Okay, not only energy, we can see everything during daytime due to the photon from the sun like this. Okay, yeah, for our mission, the nuclear fission created right now here for 2. Okay, and it's gonna be once you compute the mass difference and transform it to the energy by 131, you get 19.28. Now, the energy is in 2 digits, okay, on the order of 10 meters. Or another possible way, if you have helium-32 and helium-32 can combine to each other and you get helium-42, but without proton anymore, you get proton and proton. That would be great, right? Because hydrogen we serve as the basis for the first, second, and third processes, right? In this case, if you compute the mass difference that contribute to the energy in terms of minus 31 multiplication, you're going to get only 12, but it's considerable, right? It's in 2 digits. It's 12, and you have 19 maximum. The roughly sequential process is known as proton cycle, which is believed to be the state of energy liberation in the sun and other stars. We cannot go to the sun directly, so which is believed that this would be what's going on in the sun or around the sun. Okay, the whole three process can be again summarized in terms of figure like this. Start with the proton, you get get proton and electron neutrino, you get proton, right? And deuterium as one of the product. And in that area we have plenty of hydrogen. Hydrogen combined with deuterium, you get photon of gamma rays. And then you get helium-3 too. That's on the left side. On the right side, the process is the same. Helium-32 and helium-32 will combine together, and you're gonna get helium-42 and hydrogen, 2 hydrogen nuclei. As seen from reactions, liberated energy is carried primarily by gamma rays, photons, and neutrinos. The gamma ray are actually absorbed by this gas, raising its temperature in the gas in that area. Proton combine with electron to produce gamma rays, which is later absorbed in the gas with 3 centimeters because once proton move, they can find electron somewhere in that circumstance easily. So they're going to combine with electron and create gamma rays. Why almost temporary? The neutrino escape from the sun. Okay. You know we can see the neutrino from the sun every day. It doesn't have any effect on our body because neutrino is neutral. It's very small. It's not a big particle. It carries out only 2% of the generated energy in the fusion process there. Okay, the energy liberating fusion reactions are called thermonuclear fusion reactions. Okay, and net energy release can be created from the mass balance. When you combine everything, right, it's around 26.7. If you combine this one, 19 and 5, okay, 19 and 5 and 1, it's around 26.7 mechanical volt per process. Okay, so if you compare these amounts of energy to the one we got from uranium-235, you can see that it stays there, the energy from uranium-235, right? Because in that process you get around 200 or 208 mechanical volt per nuclei. But this one with 3 processes, you get only 26.7 mechanical volt. The sun, if the sun will continue to radiate, we can compute or estimate how long we still get the energy from the sun. Okay, your generation and my generation do not have to worry about that because of the following result. With this radiation rate like 130,000 kilowatt or 130 megawatt hour, the sun will still provide this radiation about 75 billion. Yeah. How long is that? Billion.
ใช่มีด้วยรถติด
บิลเลียนนี่เท่าไหร่นะ
เรียนก็
3,000 ล้านอะ75,000 ล้านปีอ่ะไม่ใช่วันนะ75,000 ล้านปีนะครับก็ยังใช้พลังงานจากที่ได้อยู่
ไม่ใช่ไม่ใช่ต้อง
ถ้าหลังจากนั้นแล้ว
ไม่เกิน10 นาที
ผมก็ไม่รู้มนุษย์จะอยู่ยังไงเพราะมันมีลมที่เราจะตากผ้าไงไม่รู้ไง
เปิดตับวะ
เราอาจจะไม่ใส่เสื้อผ้าอะไรนะครับเพราะไม่มีเสื้อผ้าใส่แล้วโลกอาจจะหนาวมากก็ได้นะ To exhaust this supply of protons. Okay, the fundamental challenge of nuclear fission is to give the nuclei enough kinetic energy to overcome the Coulomb force, which is a least powerful force between them and close attachment. Hydrogen and
เดี๋ยวเรา
hydrogen
ไปอะไรวะ
need to stay together and cannot fuse easily because both are need to have enough energy to let them overcome these crossing force
ไม่ใช่มันปิดแล้วแต่ผมอันนี้มันยังไม่ปิดอ๋อไปที่หนึ่งไปที่ไหนการเรียนรู้ทางความเรียน
คันเป็นคันเลยนะ5,000หรือเท่าไหร่การอันเปิดที่เขาขายใส่ไปลงตลาดนี่นะครับต้องพวกนี้นะครับเนี่ยอย่างเงี้ยต้องเปิดดูว่าที่ตลาดโอเคand the profit the profit distance is around 2 femtometer okay you need to let them stay quite close to each other around 2 femtometer in order that the execution process will happen. Okay. And to say at 2 femtometer, the potential energy of 2 protons is on the order of 0.7 megavolt. So you need to overcome this energy. One of the things is the temperature. If you use the Boltzmann formula, relation between energy and temperature, you will find that divided by 2 kVT equal to 1
จริงๆกูน่าจะว่าก่อนพรุ่งเนี้ย
ด้านไหน
for
ไป
this
ไป
กี่โมง
you need to have
ทั้งวันอ่ะเดี๋ยวหาเวลา
temperature around
พรุ่งนี้ก็ว่าพรุ่งนี้ต้องใส่ชุดเรียนได้
มันไม่จำ
Simply
เป็น
speaking, 5,000 million Kelvin.
ก็อยู่
So how can we have the device that can sustain or say that 5,000 million Kelvin?
แต่ว่าตัวที่
ไม่เราพรุ่งเรียนกี่โมง
Temperature must be on the order of Kelvin. So can
ก็แค่
include
สายเรียนรู้ว่าเรียนตอน
เลเวล
that kind of energy to overcome energy repulsion and achieve fusion. That's the challenge for nuclear
ไป
fusion.
วันไหน
But you can see that there is very little waste from nuclear fission, right? It's not so dangerous like nuclear fission. In nuclear fission, you have several
น้องไอซ์ตั้งใจเรียนครับน้องไอซ์ตั้งใจเรียน
the daughter nuclide cell from gamma ray. Okay, the reaction is made in the following deuterium, deuterium, and we have electron would provide energy around 3.2677. อันนี้ผิดนะเดี๋ยวผมแก้ให้นะ Okay, yeah, we get energy around 3.2677. And another one.
กลัวกู
Okay, the one that is promising to us, deuterium and tritium.
จัดนาฬิกาปลุก
So
11 โมง
the deuterium together
หลับ
would
เที่ยง
create
ก็ได้
tritium.
หลับตีหนึ่ง
And another possibility is deuterium together would create tritium. Tritium is the unstable isotope of the hydrogen.
10 โมงครึ่
We
งป
have
ฐมอ่ะ
the power isotope of hydrogen is one. And in this case, we
นั่น
could
สาย
get
ยากเลย
the
จริงๆกูอยากอันนี้นะสิ่งว่าเรากูอยากไปจริงๆอ่ะแบบ
energy
อยาก
difference of
มากกว่าไอ้
magnitude
แค่ธนาคารนี่
around 4 megahertz.
ดูไปไหนวะ
พิพิธภัณฑ์ธรรมชาติของจุฬา
But this is one of the things that
พวกนี้
is
ไปด้วยไม่ได้ไปบรรยายซะหน่อย
more
บรรยายให้มึงฟัง
บูรณาการเนี่ย
Another
ไป
one
อยู่
is
ค่ายไงอยู่
deuterium and
ไป
tritium.
ไปมองเกษตรอยู่
Deuterium and tritium could cause heat
คือถ้า
to
มึงเดิน
produce
ทาง MRT ก็
either
ลงพัน
food
ที่สาม
two
แยก
and
แล้วก็
one
ลง
of
พัน
one.
ที่สามแยกเดิน
In
ทาง
this
ไป
case, it's going to release energy of 7.5 T.
ที่อยู่ในอนาคต
That's
มี
more
10 ปี
possible during the energy from this process from this treatment.
ที่อยู่ในนะผมทำงานเป็นธนาคาร
And
พิพิธภัณฑ์
consequently, energy released from helium-3 to
เป็น security guard
helium gas
ไปสมัครเป็นพันโลง
เบียร์ผัก
nuclei in the fusion. What we get is
Night at the museum
helium-4 and hydrogen
นี่มันดีกว่ามะเขือเทศนิดนึง
From the mass difference and conversion by under that formula 3 1.5. We're gonna get
ที่จบคณะวิทย์ได้ไหม
Whoa. Okay, and that's all for nuclear fusion. Now we move to particle physics. Now, it's the, I think it's the last topic in this chapter. All particles nature are subject to four fundamental forces. The first one is the strong force. Second one is electromagnetic force, like we have electric charge, nuclear charge, right? And weak force, gravitational force is the active force that you can see. Once we have a mass, it's going to fall down to the ground of that object, that star, or on Earth here. Okay, let's start with the first force, which is the strong force. The strong force is responsible for the tight binding of quarks. Okay, quark is a kind of boson particle, right? To form the neutrons and protons. These kind of force is created by gluon. Okay? For the nuclear force that binds neutron and proton as well. Okay. In order to build up neutron, you need to have quark, and in order to join quark to stay together, we use the gluon, and gluon will produce strong force.
นี่ตอนเที่ยง
And in order to produce a nucleus or atom, we would have gluon as well. It's going to be in front of proton. This force represents the glue that holds the nucleon together, and it's the strong of the four fundamental forces. It is a very short range. Okay, this would take place when something is less than 1 femtometer. Now let's move to the second type, which is electromagnetic force, which is about 10 to the negative 2 times the strength of the strong force. So magnetic force is 100%, is 100 times bigger than the strong force, the force that you have in the nucleus. Okay. It's responsible for the binding of atoms and molecules. Okay. You have ion of an atom, you have negative ion of another atom is going to be combined as molecules. Or if you have nucleus and you have electron around that, electron is moving around the nucleus of the atom according to or due to the Coulomb force, right? Plus and minus, we try to attract each other. Okay, and it's a long range for us that decreases strength as the inverse square of the separation between the interacting particles. The weak force, now we like at the third type of force. The weak force is a short range for nuclear force. And that is exhibited in this instability of certain nucleus. It's involved in the mechanism of the beta decay. The strength is even bigger than the electromagnetic force. ผมไม่รู้ว่าพอไปกับเขาดีกว่าแต่ว่าผมก็ต้องพูดไปเลยเนื้อหาเป็นยังไงพวกไอ้สีฟอสมีปะในพอไปปะไม่มีแล้วแหละผมก็จับของปริญญาตรีมาเล่าให้ทุกฟังผมก็ฟังเรื่องนี้ให้ผมเอาหลับนั่นแหละไม่หลับผมเมื่อผมดูหนังสือของพอไปมันไม่มีเรื่องไอ้สีแดงนี้นะผมก็จับมาเฉยๆนะเพราะว่าคุณจะได้เข้าใจพาร์ติเคิลฟิสิกส์ได้ละเอียดเลยOkay, the V force is a shortening force, and it exists in the transition case of the certain nuclei. It's one of the mechanisms in the beta decay, and the strength is 1 million bigger than the strong force. So that's why they say it's big force, because million bigger than the strong force. Now we arrive at the last type of force, which is gravitational force. Gravitational force is a long range force, okay, because you stay here, but you still get the gravitational force from other star, from the sun, from any big object. But the strength is very big, okay, it's around 10 to 43 times the strong force. Okay, it's very extremely weak, but physics discovered that even we are very far away from those stars. This family interaction is the force that holds planets, star, galaxies. Okay, the star or the galaxy stays in its current shape right now due to the gravitational force. Okay, and it affects other element particles can be negative. Okay. You can neglect it because 10 to the 43, the digits is very far from the decimal part by 43 position is very weak actually. It doesn't make sense to keep this force at all. So by far, according to the knowledge, to the base knowledge of the physics right now, they believe that there are only 4 forces, but maybe in the future the story may change. Okay, you may or the physics may discover one more type of force. Modern physics often describe the force between particles in terms of the action of few particles. There is a special term for that is called quanta. Okay. Forces between two particles are conveyed by exchange of few quanta. So it's easy to understand that. If not, then we're going to say that it's like you transfer the money to someone. Okay, if you transfer the money to someone, the guy that who received the money would prefer to do whatever you want to ask him to do, right? Yeah, quanta is the same as the money. The particle transfer the quanta to something else that would have the effect from that guy, from the particle. This process is analogous to the covalent bond between two atoms created by exchange or sharing electrons. Now let's summarize all these things into a single table about 4 fundamental forces in physics. นะครับไม่ว่าคุณจะโตไปเรียนถึงคุณจะไปอยู่กับเด็กมันก็จะมีแค่4แรงนี่แหละที่คุณจะเจอนะครับเห็นไหมThe first one is gravitational force, okay, and the second one is electromagnetic, and weak force, strong force. You can see that strong force comes last because it's the last thing that you have learned in your life. There are 5 aspects that we are going to pay attention to. The first one is the relative strength of the time. So, ใช่ปะหมดเวลาแล้วครับหมดแล้วโอเคto not disturb your travel to be back home. So let's finish our see you in the next week, right? Bye bye ครับสวัสดีครับเดี๋ยวเสาอะไรวะเนี่ยเสาเอฟเฟกต์โอ้โหเอฟเฟกต์อะไรไม่ใครดูเว้ยโอ้สองจานไม่โทรศัพท์เอาไงขมเอาอะไรอย่างเงี้ยแต่ว่าใครจะดูสาวเอฟเฟกต์
ตัวนี้ก็เป็นต้องซื้อบ้านชอบต่อระบบกันด้วยญี่ปุ่นฮะ
เดินผ่านนะตอนนั้น
บุรีโตมึงน่าจะรู้มีทำที่อะไรแม่งมึงมาแล้วตั้งแต่ออกมาจากไหนก่อนแล้วมึงมาจาก MBK หน้ามุมนี่เหมือนที่อย่าเดินเลย
สัตว์มันมี3เฟสโอ้
ถ้าเดินมึงก็ต้องเดินผ่านไอ้ตรงคณะไอ้จิตวิทยา
ถ้าเดิน
ศาสตร์
เดินจาก
กีฬา
MBK ก็1 กิโลนะ
ขอร้องอย่าแค่1 กิโลใช่โอ้ my god bro icon ไอ้ตัว icon ถ้ามีเพลงให้ฟังมีคนให้คุยมันก็โอเคเว้ยแต่ว่า
เราจะเดินกิโลไม่แต่รอบที่แล้วที่กูเดิน
ไปดูเบอร์
ไปเจอร้าน
อยากดูไม่ดูเบอร์
เดินคิว
ไม่ไหนไม่หาแฟนหรอไอ้เดี๋ยวพวกนี้มันไม่เคยเลยมาวะจะกินมาวะมันขายป่ะ
ตายคาเลยยังเล่นอยู่เหรอ
เฮ้ยฟอด